I can continue with my lectures, and but what I said is that
I'm sorry to interrupt, but don't forget to share your screen.
Right. Yeah, that's why I'm stopping, because I noticed you wanted to say something. Right, so let me share my screen. So we want to understand representation theory of a VOA, and we decided, or I decided that the one to look at are admissible level affine VOAs, and that turns out to be difficult, so we restrict to the low rank case to SL2. Now, understanding the representation theory first amounts to deciding which category of representations you want to look at, and then you want to establish certain properties. So we decided to look at the category that is as large as possible for two reasons. If we want to have a tensor category, and if we go smaller, the only tensor category we could have is the category of ordinary modules, and that one is not interesting enough. So then we were able, so the results that I so far presented are classification result of the abelian category, classification of simple modules, classification of projective modules. So that means very good knowledge of the category as an abelian category. That's very good. And then what I presented yesterday is the idea how to prove that you have a tensor category structure. So we also succeeded with that. Now, I'm also presenting all these things not only because the results I think are interesting, but also because I think the methods are quite interesting. Right? It's it's in general an open problem and an important problem to classify good categories of modules of affine vertex algebras and W algebras. And these techniques, they will generalize partially, so it's good to be aware of those. Anyway, if one now completely wants to understand the category, then one would understand now more detailed structure of the monoidal category. So what does this mean, more detailed structure? You would like to know some fusion rules. What are the explicit tensor products? And what else do you want to do is usually you also would like to prove rigidity. Now, these problems are difficult, and so Robert McGrath and Jinwei and I, we will have a coming paper where we completely solve this problem for 2 levels. And I will not talk about that paper. I thought a lot about how to get fusion rules, and it's a tricky thing. It's really a tricky thing. And I want to tell you one trick how you get some fusion rules today. And you get those whenever you have a good coset realization. So and you will see again quite sophisticated theorems go into the story. So we continue with SL2. Now I fix the level k-1 to be admissible. So and then in particular k itself is admissible, and I parameterize it in terms of the shifted levels u over v as before, just to have the parameters. So then there's this famous GKO, Goddard, Kent, and Olive Coset Theorem, 3 physicists who found the statement that if you take the affine vertex algebra of SL2 at level k, or let's say k-1, times the simple affine VOA of SL2 at level 1, that's just the lattice VOA of the root lattice of SL2, then you have a diagonal action at level k, and then one can ask, what's the coset, what's the subalgebra that commutes with this diagonal action? And they notice this can only be the Virasoro algebra and nothing else at the corresponding central charge. But not only that, the statement, that's the statement for the universal affine VOA. Also, if you go to admissible level, well, they actually only went to integer level, and you do this coset for the simple quotient, then you get exactly the unitary series of the Virasoro algebra, the unitary Virasoro minimal models. And of course, physicists like that a lot. And then a few years, Arakawa, Linshaw, and Ivy, we proved this Coset Theorem in big generality for principal W algebras, which is quite important for generalizing what I'm saying here. Anyway, so let me write down this Coset statement in a certain way. So we take the simple affine vertex algebra at the admissible level k minus 1. We tensor it with the lattice VOA of SL2. It's the affine vertex algebra at level 1. So then we have a diagonal action at level k, and this action is given by the simple algebra at level k. And now I used the notation of my previous lecture. Remember that I denoted an ordinary module, a module whose top level is a finite dimensional representation of SL2 by LR, where R denotes the dimension of the top level. And so these are here, I give it a superscript k to indicate that this is at level k. And the Coset statement is, the refined one is that we have here a decomposition of this type. The sum goes over all admissible weights that lie in the root letters. And what is this M? So by M1, 1L, I denote the simple Virasoro algebra. It's rational at this case as a minimal model at the central charge, well, given by L. So this means then the formula is always this one. It is 13 minus 6 times the shifted level minus 6 divided by the shifted level. And here L and K, well, you can write it explicitly what they are, but the instructive formula to say how they are related is that the inverses of the shifted levels add up to 1. Anyway, if we write, remember we wrote K plus 2 as U over V just upstairs, and then I write L plus 2 as U over W, where here W needs to be U minus V. In particular, if you require K minus 1 to be admissible, we require that U is at least equal to V plus 2. Okay, now this Virasoro algebra has simple objects. The simple objects of this Virasoro algebra I denote by an subscript R, S, which should remind you a lot of the subscript of the highest weight modules of SL2, this D plus. I denoted them in my lectures always also D plus, the subscript R, S. So the reason for this, the same labeling, is because the Virasoro algebra is the quantum Hamiltonian reduction of the affine vertex algebra, and these D plus R, S are mapped exactly to these Virasoro modules under quantum Hamiltonian reduction. So it has these simple objects where R is an integer between 1 and U minus 1, and S is an integer between 1 and the denominator of the shifted level minus 1. This denominator I denoted by W. Okay, now it turns out there is a Weil reflection symmetry, which in the Virasoro case means that these are not all non-isomorphic, but one has this isomorphism. Not that important for us today. Now, the Virasoro algebra is a rational vertex algebra at this admissible level. I think Wang was the person who proved that first. And the fusion rules of these are also very well known. Well, I have to admit, I don't know who did this first. So if anybody knows, let me know. It's just like I forgot.
I think Wei-Xiang Wang also did fusion rules.
Yeah, thank you. So
as well as rational.
Yeah, that makes actually sense. So this is then to give him credit here. This is due to Wei Zhang. How do I pronounce his name? His first name?
I think Wei-Xiang Wang.
Wei Zhang. Okay. I always have problems with pronouncing names. Okay, so the fusion rules, but one also should say that the physicists knew these fusion rules for a long time. So the sum is always over all allowed labels. So I don't indicate this. And then one has here these famous fusion coefficients denoted by an n with all the labels in there. And one has one such factor for the numerator and one for the denominator of the shifted level. And then one has this formula, and now and these numbers, these fusion coefficients, they are very well known. They are either equal to 1 or 0. 1 if a certain condition satisfies, right, and otherwise 0. And this condition is that absolute value of a minus a prime plus 1 is less or equal to a prime prime is less or equal to the minimum of the two numbers, this one and this one. And in addition, we also have the condition that the sum of all three labels needs to be odd. So the sum of all labels being odd is a condition that that the fusion product preserves the coset of the root lattice. So that's something very natural from leaf theory, and also this product is clearly a truncated tensor product of SL2, right? So if the tensor product rules of SL2 is are exactly of this type if I don't take the minimum but just up to a plus a prime minus 1. And this funny shift by 1 is due to this maybe unfortunate notation that people use for Virasoro. Well, this notation, let me also say that it comes from physics. And it's not bad because this shift by 1 is a shift by the while vector. The while vector of SL2 is the fundamental weight. And this notation means you don't use the weight label itself as the label for the module, but the weight label shifted by the while vector. And it turns out for W algebras, that's quite a meaningful label. So it's not only a physics notation, but it's also one that is not totally unnatural from a conceptual point of view. Okay, so why am I presenting this? Because we get one fusion rule for free now if we know enough background. And so this is not a new theorem. This is Jinwei, when did we do this? 5 years ago, 6, 7, I don't know. So these are the fusion rules of ordinary modules. And I thought I start by presenting this because by this I also can explain you quite a few things about an interesting theory. So the theorem is that the ordinary modules of SL2 at admissible level have the very same fusion rules as the integer level case, as long as the numerator of the shifted level coincides with the integer plus dual Coxeter number. So these are the same fusion rules. So that means let me write this down. The affine vertex algebra at level W minus 2, SL2, has the same fusion rules. Note that this doesn't mean it has the same tensor ring. That depends on the denominator, whether that's is also true or not. Okay, so I now want to spend quite some time on telling you how to prove it. And just because we need interesting generalities. And yeah, I think, I mean, some people have seen the proof, like Jinwei probably has seen it, I could imagine. but most of you surely not so. And the nice thing is this this follows from the categorical framework. And let me set up the categorical framework. So this is what I will now be explained. I think it's yeah, I think it's instructive to see this again. So we start with a braided tensor category. So, and you think about it, of course, as a category of modules of a vertex algebra. And then we want to use tensor category theory to relate fusion products of one VUA that we know. So here, in this case, we know the fusion products of the Virasoro algebra to fusion products of a VUA that we don't know, but that are related via some explicit construction like this Coset construction here. Right, so here we have the statement: we know Virasoro algebra at level L at the central charge. We don't know the affine VUA at level K and K minus 1. Level 1, of course, we know perfectly fine. That's super easy. But we hope that we can say something about the fusion rules by just comparing just from the knowledge of Virasoro. And this is indeed true, and it's true, but only true for the category of ordinary modules, at least for the moment. And the framework is called, well, we are looking at, we rephrase the problem of VUA extensions in categorical language. So what do we have here? We have a small VUA, the tensor product of an SL2 and Virasoro, and we have a big VUA, that SL2 times the SL2 at level 1. And we want to think about this big VUA as an algebra in the category of our smaller VUA. And we would like to have a monoidal functor from our small category, in particular from our Virasoro category, to the category of modules of the big one. So you should think about this as a categorical version of base change of commutative rings, right? A tensor category you think about as a categorification of a ring, a braided tensor category as a categorification of a commutative ring, and now this object of VUA, this procedure of VUA extensions rephrased in categorical terms, you should think about as a categorification of base change. Anyway, so and we don't call it a ring, but we call the corresponding object an associative algebra in the category. So, and what is this? It's A itself is an object in the category. And then M, well, what do we need? We need to have the same. What is an algebra? Usually it's a vector space with some multiplication. So a vector space we replace by object, multiplication, a morphism from A times A to A. And then we wanted to extend our, to extend our smaller algebra. So in particular, we want our smaller algebra to be included in there. So that means the tensor unit we wanted to embed in A. And now we want this, we want the product, we want this to be an associative algebra. So we want the product to be associative. Well, what could this possibly mean? We have the associator that just tells us that we take our tensor product in different order. Put our and now what could we possibly do here on the left-hand side? We can, of course, do multiplication on the second factor. On the right-hand side, we can do multiplication on the first factor. In either case, it's a map to A times A. And of course, from A times A, we can go to A via another multiplication. And we say this algebra is associative if this diagram commutes. And so that's the obvious thing. And then you also want to have compatibility with the unit. What can you have here? You have here 1 times A. You can embed it in A times A using your iota. But in a tensor category, you have the left unit constraint. So I call it here LA. And we have here our multiplication map, and compatibility with the unit is commutativity of this diagram. Same thing for the right unit. So let me also quickly write this just because it doesn't take time. So you want to have the same type of diagram. Commute. Okay, now this is the notion of an associative algebra. Now we assumed the category to be braided, and if it's braided, you can also have the notion of a commutative algebra. The braiding is the commutativity constraint in the tensor category, and so we say our algebra is commutative if the algebra multiplication commutes with the braiding. Right, the braiding maps A times A to A times A. It's not the identity map in general. And so commutativity, this is a highly non-trivial constraint that this diagram commutes. Right, and so this in particular, it's somehow quite rare that an associative algebra in a braided tensor category is also a commutative algebra. But the commutative ones are what we are interested in, because the commutative ones are exactly what describe the category, are the categorical counterpart of VOA extensions. Okay, and now we want to categorize base change. Base change also maps, of course, modules of your smaller ring to modules of your bigger ring. And so first of all, you have to say what's the category of your algebra. So the category is denoted by a C with sub-index A. Often it's also denoted by a rep A, whatever you prefer. So this is so what could this possibly be? The objects, we don't really have a choice, but what can they be? They must be pairs where X is an object in our original category. But it must be an object that has a natural action of the algebra, right? You want it to be an A module. And so what could be such an action? It must be a morphism from A times X to X. And then subject to the constraints that you can write down. Right, so we have the same thing as before for the unit constraint. We can embed 1 times X in A times X, but on the 1 times X we have our left unit constraint. A times X is mapped to X via the multiplication, and you want this to commute. And then what else do you want? You also want to have the natural associativity property. So what you do is you write down the product of A, and X. You can bracket it in 2 ways. These 2 ways are related via the associator in your category. And now you can multiply here on the left. We can use the action of A on the algebra to go to A times X. Here on the right, we can use the algebra action on itself to go to A times X as well. And now you see we can use the algebra action on both sides again to get a map to X. And this you want, and this is the constraint, the associativity constraint for modules. And you see all these things, of course, naturally are the natural things that you can write down in a categorical way, which of what you know, for associative algebras. Now, what the problem for the VUAs is that this category CA is too big. The problem is, while even though C and the original category is braided, there's nothing that guarantees that CA, the whole category of A modules, is braided again. It inherits a tensor structure from the original category, but it doesn't inherit the commutativity constraints. And so it turns out one needs to go to a smaller category. Remember that A is a commutative algebra. Yeah, let me recall that A is commutative. And this CA local, that's the subcategory that is braided. And here is the subcategory of objects that satisfy an additional commutativity constraint. Well, the problem is the algebra x from the left. So I cannot, the braiding would map a times x to x times a. So what I'd have to do here is I have to apply the double braiding. It's usually called the monodromy. So this is why I just write M for it. So that's the composition of one braiding, right? The first braiding maps a times x to x times a, and the other braiding maps it back. And recall that in a tensor category, in a braided tensor category, this monodromy is usually not the identity map. So in particular, I can now left and right hand side, I can apply the action of a on x, and this to be a commutative diagram is quite a severe constraint. So usually this category of local modules is quite a bit smaller than the big category. Anyway, now with this setup, we have a functor that does the base change. It's called an induction functor. And what does it do? It's a functor from C to our category of A modules that maps X. Well, it needs X to needs to map X to an object on which I can naturally define an action of the algebra. So what could I do? I could just take the tensor product of A with X, because then I have a multiplication map that is just the multiplication on A composed with the identity and times the identity on X. And this functor is a tensor functor. In fact, it's even more if you have an object, if you restrict to the subcategory of modules of C that induce to local modules, then it's even a braided tensor functor. Anyway, so you see, I could also have started with these generalities before, but I'm setting up all this generality because I want to explain to you that this theorem actually follows immediately from existence of tensor category together with the VOA theorems that we have. And so let's see what's the, and this whole story started with a very good paper by Huang, Lepowski, and Kirillov. Huang, HKL, Huang, Kirillov, and Lepowski. And it says the following: we have a VOA and a VTC, vertex tensor category, a braided tensor category of VOA modules. And then the following statements are true. We can have a VOA extension. By VOA extension, we mean we have an object W in our category C that itself is a VOA that contains V as a sub-object, and the and if just the vertex operators restricted to V are the original ones of V. So we want this W to be an object in C, and such VOA extensions are equivalent is this is HKL, and then Shashank, Robert, and we met more than 5 years ago, I think, maybe not. So I think so, 6, 7. And Shashank, you were here, and Robert was visiting, and we noticed that this theorem is really, really good, but it's not useful enough for what we want, because you also want to have the rest. You want to have that this category of local modules is in fact the same as the category of A modules in C. This is what Huang, Kirillov, and Lepowski also proved, so I should have attributed it to them here. But we also want that this category of local modules is the same as the category of W modules as braided tensor categories, not only as abelian categories. And that's a huge difference, because then you can study the monoidal structure on the categorical level. And we of course, and this is what we proved in this very long paper that some of you might have seen, that this category of local modules is equivalent as a braided tensor category to the category of modules of the VOA, of the big VOA. So, and in particular, this induction functor I presented is then also a vertex tensor functor. So this is Shashank and Robert. Okay, so these are the generalities I wanted to present, and you see it took a bit, but I think it's nice to have seen it. If you haven't seen it, then it's definitely nice, right? You saw how to categorify rings, etc. And if you have seen it, it's hopefully a nice review. This theorem in particular, that we have this equivalence of braided tensor categories, has been turned out to be enormously useful, and in particular these fusion rules that I presented above, the theorem we want to prove follows. So this theorem follows now immediately, totally immediately. So why does it follow? Let's now do our theorem as an example. And that's then also the proof. So in our example, we have our category of our small category is the category of, it's in fact quite a big one. If we take the category of weight modules, the linear product with the category of modules of the Virasoro algebra, and the corresponding small VOA is of course just the tensor product of the two VOAs, and the big VOA is SL2 level shifted by -1 times the lattice VOA, right? The very first thing I presented today, the GKO Coset Theorem, tells you that this tensor product of these two SL2s is a big direct sum of modules of V modules here, right? So let me maybe repeat the sum here, right? It's it is this sum. Yeah. One thing that is kind of the key thing here is to notice that this label here is 1. So that's why is this important? Because let me maybe write down one fusion rule. We have this fusion rule. So by box times I denote fusion product, and by tensor just a tensor product of vector spaces or E of VOAs or VOA modules for different VOAs. The fusion product if between two modules where one module has a trivial label on one side and the other one a trivial label on the other side. Remember, one corresponds to the tensor identity, and the fusion product is just a simple module where the labels are what they should be. So why is this so useful? Because now I have a functor from Virasoro, but only from what you should call the right category. So the right category is where the left label is trivial. The left label here is a 1. So what can I do? First of all, I can embed this module in my view. I can make this map this to a V module by just tensoring it with the affine VOA of SL2 at level K. Right. So remember, this L1K stands for the affine VOA. And why can I do this? Because now I can apply this induction functor. And I omit the algebra action because we don't need it. I just write down what it is as an object. Right, so what is it as an object? It is the tensor product of A with this module and the tensor product in V. So it's right, this is A box times this module, this V module. And now we write down this explicit form of A. Right, it is it is all these simple while modules. And let me now leave some space here times the so module. And now taking tensor product means, of course, here I have to take the tensor product with the affine VOA, where that's just the tensor identity, right? And here I have to take the tensor product of so modules. And now you see this is nice. The summation here is always the same, right? Because here I just get the LR again, and here I get this so module. So it's a very simple sum. And now maybe I'm lucky and I can identify with this with a module of the big VOA. And indeed, because the branching rules are completely known, it's very well known simply that this is isomorphic as an A module, as a module for the big VOA to the module of the affine VOA of SL2 at level k minus 1 at weight label S, so at weight S minus 1, times the module of the lattice VOA at weight label S bar. And here, let me just tell you what S bar is. S bar is equal to 1 or 2, depending on S being odd or even. So it's also not very important what it is. Right? And why is this so helpful? Because every map here is a tensor functor. Of course, mapping M to the tensor identity times M, that's a tensor functor, right? So it's just the embedding of Virasoro category inside the SL2 times Virasoro category. And then this F is a tensor functor as well. So the composition is a tensor functor. And so in particular, we get now, we get the theorem for free, right? Because now what do we have here? We want to understand what's the tensor product of the admissible affine VOA modules. Well, if I tensor this with a module of a lattice VOA, I don't really hurt myself, right? Because I know the fusion rules there. So this L1, remember, is just the lattice VOA of SL2. So now the previous computation has simply established that the first object is the induction of the image of the induction functor of this module, this V module, this module for this subalgebra. And similar for the second vector. And now here I can use now that the statement that this in fact induction functor is a monoidal functor. This means that this is the same thing as taking first the tensor product of the modules, of these V modules. But now you see the first factor is just the affine VOA itself. So so this so in particular, this is just given by the Virasoro fusion rules, which and now I use again that I already know what this induction is, right? This is the computation we did before. I mean, it's this one with S replaced by S prime prime. So that means it becomes And here we just have to worry, the lattice VOA is not important. And from this, the theorem follows immediately, right? So yeah, so here, this is the first part for today. And it tells you that one type of fusion rules we get under two conditions. So, well, so the basic assumption is that we are aware of these generalities about tensor categories, and in particular, that we are aware that there is this really nice theorem that tells us that the categorical means are the same as the VOA means, so that we can use the techniques of the tensor categories and in particular of algebras in tensor categories. And then what else do we need? Then we need a relation of our VOA of interest to a VOA that we know. For example, here we are interested in the affine VOA of SL2 at level k-1. Well, if we tensor it with something very well known, that is VOA, it turns out then it is an extension of a Virasoro minimal model times another affine VOA. This other affine VOA we don't like so much because we also don't know it, but it turns out already knowing that we have a tensor category structure is enough to establish this theorem, right? The only thing we used about this affine VOA of SL2 is that we know that we have tensor category, which in fact for the category of ordinary modules we already established a long time ago, and then we can apply this whole framework. Please ask questions if you have any. Okay. Any no questions? Okay. And now we try to do more, and there's one thing I could come up with. So let me sketch it, and you already see, you will see that this is again very much like this theorem I just presented. I presented it for SL2, but the technology clearly works in quite some generality. And in fact, using the Coset theorem that a simply laced affine VOA times its lattice VOA is related to its principal W algebra, one can establish the same type of theorem for any admissible level affine VOA of simply laced type. And so it's the same argument. With, of course, more work, but in principle, the same argument. So anyway, so now I want to present, first of all, a refined Coset theorem. It's called the Urort or translation statement. It's probably much less known. It has a fantastic geometric motivation. And I don't write it down as a precise theorem, but I write down the slogan, and I will illustrate it in the example relevant for us. So sloppily speaking, the theorem can be said that the quantum Hamiltonian reduction functor commutes with tensoring with integrable representations. And I don't want to introduce all the notation to properly formulate this theorem. It would actually not be too much, but it's enough to illustrate it in the example. That is, I think, so that we need. So, and this is a theorem of Arakawa, myself, and Boris Fagan. And yeah, let me first state it in the SL2 example, and then maybe lose a few words on where it's coming from. So what we, first of all, let's maybe recall a little bit about quantum Hamiltonian reduction. This is something that is, one doesn't need much in order to introduce it for SL2. What you do is you take your affine VOA, and then you want to make the affine VOA into a complex, which simply means you add free fields, usually free fermions, but sometimes also free even fields, but beta gamma systems. Anyway, in the SL2 case, you just add a single pair of free fermions. I call them B and C. Remember, I did this already yesterday. B and C was the notation for pair of free fermions. And why do I do this? Now, now I would like to have a differential on this complex. So what do I need is I need an odd field. And you take the odd, just one of these fermions times E plus 1. So what you want to do is you somehow want to do some gauge fixing procedure that fixes E to be a constant, E plus 1 to be 0. So, it is obvious from the SL2 OPEs, right? E has trivial OPE with itself, B has trivial OPE with itself. So in particular, the OPE of D with itself is 0. In particular, its 0 mode squares to 0, right? It's a and yesterday I also had already discussed some homologies of VOAs. In that case, it was how I relate two different VOAs, SL2 and super Virasoro algebra. Here it's similar, but here now I want to go down from SL2 to Virasoro algebra. Anyway, if you have this, you can, so you know you have a complex, your VOA times the ghosts, the fermions, and you have a differential, so you can take the kernel of this denote modulo the image, and it turns out in this case, this is just the universal. In this case, this is just the universal affine VOA, universal Virasoro algebra. At the same central charge that I always write down 13 minus 6 times the shifted level minus 6 divided by the shifted level, shifted by the dual Coxeter number. Okay. Now we want to refine this a little bit. So now what can we do? We can also take now not the affine VOA itself, but a larger algebra that carries an action of the affine VOA at level k. For example, the affine VOA at level k minus 1 times the integrable one at level 1, right? Level 1, that's the integrable ones are the ones where the simple quotients where the level is a positive integer. And I can again make it a complex in adding my two free fermions. And now I can write down two differentials, and now I give them a superscript. So this k minus 1 indicates that it's only acting on the first factor. And so what is it? It's the same thing I wrote down as a few seconds ago, where here now the E is the E of SL2 inside the first factor, the level k minus 1 affine VOA. But I can also write down an odd field at level k, namely this one here, where my E tilde is the E in the lattice VOA, right? So then this decay corresponds to the quantum Hamiltonian reduction for the diagonal level k action. And now this translation theorem says, well, the slogan was quantum Hamiltonian reduction commutes with tensoring with integrable representations. L1, SL2, that's an integrable representation. And so the statement is then that I have here two complexes. I mean, the complex is both times the same, but I have two differentials on this on the same complex, and the statement is that their homologies are the same as vertex algebras. And so these are here the same as vertex algebras, but no O conformal vectors are different, or you have to change the conformal vector on your lattice VOA to make this an isomorphism of vertex operator. So and it's quite a sophisticated isomorphism, right? It's so you'll have quite a hard time to check this by hand already for this SL2 case, even though there everything is so explicit. Okay, now why do I present this? Because and in particular, what does that have to do with fusion rules of SL2? Well, you'll see in a moment. So what can I do now? I can apply this. So it gives me, first of all, a new Coset theorem. Well, I can take the Virasoro algebra is, of course, just the quantum Hamiltonian reduction of SL2. And so so here, right, this reduction only acts on the first factor. But the Urart theorem tells us that this is the same, the reduction on the same complex but with a different differential, right? And this now I can insert the Coset theorem, and so here I don't write down the precise sum over R, but here we have our while modules at level K. Then we still have our goes, and let me write here the differential already, and the Virasoro vector is just a spectator because it's the diagonal action at level K. It doesn't act on this. The Virasoro module is just a multiplicity space. And now we use that the reduction of a while module is the Virasoro module with these labels. And we get quite a funny Coset theorem and in fact branching rules. So you get, well, Virasoro at level K-1, for example, tensored with this integrable representation. And this integrable representation in this case is called the Urart. So that's it's Boris, he invented this name. He thinks it's a fitting name. It turns out is then equal to a direct sum of Vir times Vir modules at different levels. Okay, so the geometric interpretation of this is quite fantastic. So I'll make a short excursion on that just in words, okay? I will not write anything down because this will be too much. So there's this famous AGT correspondence. And this AGT correspondence is about something called, the physicist calls pure super Yang-Mills in 4 dimensions. And that can be, and that has a quite an explicit geometric notion. It's a moduli set base of certain sheaves on CP2, sheaves with some framing at infinity. And the AGT correspondence says that the equivariant cohomology of this moduli space of these sheaves with some framing at infinity is a Verma module for a W algebra. So, and if you you have an SL2 SU2 action, then it's the W algebra of SL2, the Virasoro algebra. And that is that was the AGT conjecture translated into mathematics and proven by a really nice important paper by Schifrin and Vassaro maybe 10 years ago. And but then there's you can also do a blow up at infinity for your for your geometric problem, and then you can ask what happens to on the geometric side, and it turns out well, at least this partition function, this norm of the fundamental class, enjoys a nice property that it blows up in the sense that it becomes an infinite sum of products of partition functions. And why does this work? Because the Verma module times this ORD is a direct sum of Verma times Verma module. This means the Whittaker vector in your Verma module becomes a direct sum of Whittaker vectors in your in the Verma modules for the two Virasors, and then taking norm, your partition function becomes a sum of bilinears of partition functions. So this means this identity was conjectured because you wanted to make this Nakajima-Yoshioka blow up in 4 dimensions of these instanton partition functions. You wanted to understand the corresponding 2-dimensional version, and this is it. So a really nice interpretation. Not important for us today, but really nice. Okay, so now in general, one also would like to understand what happens for modules, and the theorem is quite similar. So here, let me write down the formula. And if I take now a Virasoro model that has these 2 labels R and S, and now I also do it in an admissible level, and then one has here one more condition that S plus 2T plus R needs to be odd. Anyway, so why do I need this? I need this for the following reason. So I have presented this already twice. This what Dražen Adamović told us, that SL2 embeds inside Virasoro times this pi naught. This means an SL2 module embeds, if it's nice enough, in a Virasoro times a pi naught module. And in some time, and in most cases, it's in fact not only an embedding, but in fact an isomorphism. So that's this holds in particular for these typical modules. So it turns out via this embedding of SL2 inside Virasoro times pi naught, this typical module, or relaxed highest weight module, twisted by some spectral flow, is nothing but the Virasoro module that has exactly the same labels times a certain pi naught module. Remember, this pi naught was this half lattice VOA, an extension of a rank 2 Heisenberg VOA along a diagonal isotropic lattice. It's not important for us what it precisely is. Why is it good to have this embedding? And let me also, for one more case, if this weight was very special, it is this very special level lambda r comma s, then in fact this E minus is not simple, and it fits into this non-split short exact sequence. Now, why is this so good? Because what can I do now? I can combine this observation with the UROT. I should note that and now I just tensor it with a suitable level 1 module. That's just in order to make the summation nice. It's not that important. Oh, and I shouldn't call this sorry. This index here is not an L but an N. And now I can, but now I can apply the theorem I presented before, that one also has a Coset theorem for Virasoro, So then this becomes the sum. And I only used this funny, I mean, this labeling of the SL2 level 1 module so that I can always do the summation here over R odd. Okay, but now I can use the statement of like I of course have to make sure that the embedding of SL2 at level k minus 1 and at level k of Trajan is compatible with this Coset theorem, but it is. One can check that, and then you immediately get this decomposition. So this means what this Coset theorem that Virasoro times this lattice VOA is a direct sum of Virasoro times Virasoro together with Adamovich nice construction immediately tells us how a relaxed highest weight module of SL2 times an SL2 at level 1 module. Here this is here we have a module at level k minus 1, and here we have a module at level k. What the branching rule is, how is the decomposition into level k SL2 modules times Virasoro module. And in a very similar way, you can you can prove this for the other types of modules. So for example, one has the projective modules, and you have a very very similar type of statement.
Hi, Thomas. Here, the last formula, it does not need R is odd.
Yeah, it needs R's odd, yes. The summation is always the same.
Yeah.
It's so I so we always get such a nice decomposition, and similar for the for the D plus modules. Maybe I don't write it down because it's exactly the same type of thing. Okay, so now I'm claiming that I get some fusion rules from this decomposition factor, from this decomposition. So why is that? Let's think about it. What do we? I want to do a kind of a similar trick as before, but I can't use any. I can't use these categorical methods because I don't know. I don't know any fusion rules of SL2 yet, except the ones for the ordinary modules. So what can I possibly do? So first of all, let me tell you a few well-known properties of intertwining operators. Or in fact, I didn't find them in the literature, but they are very easy to prove. I mean, it follows relatively immediately from a statement in the book by, I think, Tong and Lippost. So if you have an intertwining operator and you have that in the intertwining operator acting on a vector is 0, then it follows. So they phrase it that then the intertwining operator also must be 0, and that is true if all involved modules are simple. But we have here now the problem that we have modules like this P and our atypical relaxed highest weight module that are indecomposable but not simple. They are indecomposable but reducible. So we have to be a little bit more careful how we phrase this statement. And so it follows that Y does not need to be 0, but at least it is then 0 for all vectors in the module generated by M. The M module, I mean the V module generated by this vector M and all W in the module generated by the vector N. And a consequence of this statement is that if these two vectors already generate the whole modules, this is which of course, if you look at our case, right, the simple modules are of course generated by any non-zero vector, but these projective modules I wrote down, they have this projective cover, they have 4 composition factors. And as long as I had to choose a vector that is in the top level, meaning I choose a vector on which the Virasoro zero mode does not act semi-simply, that's the description of such vectors, then it also generates the whole module. So then the image of the intertwining operator is the module generated by the collection of vectors VKL. And what are these? These are those vectors that appear in the action of the intertwiner at M acting on N. So then we can always expand this. Let's remember this can possibly be a logarithmic intertwiner, so logarithms can appear. Anyway, so why is this so important? It has corollary is maybe overkill, but we get the following fusion rule out of it. We can take an ordinary module and we can tensor it with, let me call this module n1, t, and we get that this fusion product needs to be ns, t, where here I take n, my notation for ns, t is one of them. It doesn't matter which one I do. I take it, it's just that the labels of these modules need to be s and t. So it's one of this of the collection of these modules. Now and it turns out now fusion product is associative and commutative. So by this formula, you get in particular that the collection of modules n, s, t, where s goes from 1 up to this w minus 1, they form a module category for the category of ordinary modules. And in fact, as a module category, it's equivalent to the category of ordinary modules as well. And I would also, it seems that this, so we are actually quite interested in module categories now, we being Shashank, Robert, and Jinwei, and so yeah. Anyway,
is this sorry, I should say, are these results mainly because there are some commutative property between the spectral sequence, spectral flow and the intertwining operators, like Heisenberg's delta operator has such kind of properties?
No, I mean, yeah, you have this Heisenberg operator. I actually could also have mentioned that, but no, these are have this argument has nothing to do with that.
Okay, thank you.
It's yeah. So let's see. Let me start by doing a computation that gives you the idea. So let's what do we do is we take an intertwining operator of the desired type. So let me write here some big brackets. We take here our ls, we take here our n1, t, and then here we take r, and we want to determine what could possibly r be to have a non-zero intertwiner. Now, and now we want to use this Coset theorem. So we tensor this with a suitable modules of the the lattice VOA. And of course, we can do this. The knowledge of the intertwiner of type LS and 1, TR is the same as knowledge of this intertwiner. Yeah, we can assume this to be a surjective intertwiner if we want. And we might like to put a restriction on n, and it turns out it's probably good to start with the projective modules first, just because projectivity is a good property. I'm actually not sure how much I need it, but in the explanation, it follows best first for the projective ones. Okay, so now let's think about what we know. So first of all, and maybe I give the superscripts, and again, that we don't confuse ourselves. These are modules at level k-1. This is a module at level 1. And recall that I have this decomposition. And why do I choose this module n1, t? Because what's the property? It turns then here we have an nr, t, k times m r, 1 l. So I choose this 1, t because then the label here is trivial. That's the key thing. Very, very similar to the first part of my presentation. Why is this key? Because let's look at submodules that are interesting here, right? Here we have on the left-hand side, the tensor identity in there as a factor, as a summand, and then the right summand is an m1, s l, right? And here we have as a summand the module nr, 1 times the Virasoro algebra, right? Remember, 1, 1 is the notion for the Virasoro algebra in itself, right? So you see, what can I do? What do I want to do? Is I want to use this lemma where I choose v and m and n, m and n to be vectors in these two summands, right? Because what do I have then? Then my intertwining operator, of course, restricted to these direct summands, must be an intertwining operator of the subalgebra of type VOA times module, the left VOA times the module for the right VOA, and the other module is a module for the left VOA times the right VOA. Of course, we have only a single intertwining operator of that type. So this means the restriction of our curly y to the summand, we simply know what it is. And that's the whole point of the story. So this means we restrict to a vector v in the good summands. And we note that, of course, as long as we, if I mean vector, I mean non-zero vector, and any non-zero vector generates the whole module, right, as a module for the big VOA, since this is a simple module. Now, what about the second summand? Here, I'm not totally free in choosing this vector W, because so what do I have? I have two cases. I assumed this module n to be projective, so it could be simple and projective. In fact, most of our ones are simple and projective. So if this is simple, then the same thing is true for the corresponding module with the same labels, but at level k, and in particular, W generates this whole module. right? And otherwise we have n1 comma t k minus 1 is generated by any vector w if L naught acts not semi-simply on W. So this means we have to choose W to be a vector on which L naught does not act semi-simply and being in the subspace. But we know we can do that because we have the decomposition formula, and we know this is such a module. Okay, but now we see that we have so now what follows, right? We have now we can apply our previous corollary. We have right, whatever we know is the previous corollary tells us that R, I assume this intertwining operator is surjective, so the corollary tells us the image of this intertwining operator is equal to the module generated by these two vectors. In particular, it is an SL2 at level k minus 1 times SL2 at level 1 module that is generated by a subspace of that as a module for the subalgebra is just this module. Okay, and then I claim that it relatively immediately follows that R needs to be ns comma t times the corresponding SL2 at level 1 module. And then, and if this claim is true, then let me note that the statement for non-projective modules follows quite easily. Follows because one knows that that these, by exactness of tensoring with these modules, with these ordinary modules. And why is this exactness tensoring? Because we know that these ordinary modules are rigid. We have rigidity, and then we have this property. Okay. Yeah. Shall I explain the proof of the claim? So really, one has to formalize it, and so so this claim follows from two lemmas, and both lemmas are longer to formulate than proof, actually. But I only formulate it. It's really more. What do you need? So let me maybe write down these lemmas, and then then I've told you everything I wanted to explain to you. So let's simply formalize the situation. We have a small VOA, that's the tensor product of our SL2 and the VRSO, and a big VOA, which is the SL2 at level k minus 1 times the lattice VOA. And this is here as a VOA extension. And let's maybe, to be safe, in a finite length category with enough projectives. So I need that every object has a projective cover. And this is a property we have established for SL2. Now we take L as simple and rigid V module, like our LS, and P a projective indecomposable ones, like our N1 comma T. And so then let L be a direct sum over some index as a set of Li of W modules, and P direct sum of also a direct sum of W modules. Now, assume that we know the fusion product as W modules for a summand. Right? I'm really only formalizing the situation of what I've done before. So the fusion product of two specific summands is just well-known third module, which I call here R1, and that this summand is projective and indecomposable. So with another property, with the property, so I do an enormous amount of assumption that this projective module, of course, it surjects on some quotient x1, and this quotient has we wanted to have the unique property. I mean, the unique property among all homomorphic images of R1, that there exists a simple module for the big VOA that has this module x1 as a direct summand. So if all these properties hold, so really a zoo of assumptions, and these assumptions are simply a formalization of what we know for our example, then it follows that the product of the fusion product of L with P must be equal to the projective cover of the simple module X with a certain multiplicity. The only thing is we don't know is whether this multiplicity is 1. So, and I don't prove this lemma, but it's
So this x1 is a direct summand, but x is already simple. So this
no, x is a simple V module for the big VOA, and x1 is a direct sum in the decomposition of x as a W module.
oh, okay.
Right here, W is the small r. Yeah, V module that has x1 as a direct summand as a W module. Yeah, good question. So in particular, the claim follows if I can show. So I almost got the claim. So at the moment, I proved that one has this statement here, where just that we still now have to show that this multiplicity is equal to 1. And in principle.
So Thomas, may I ask you a question? So this n, is there any way to determine this n using the multiplication of n px, the coefficient n? You mean L tensor p equals n px for some n, right?
Yeah.
So my question is that this n somehow depends on something. Do you know?
Yeah. So I think I would find it
Is
hard.
there any clues on this n?
Yeah. So I will prove. I'll tell you now how I know that in this case n is equal to 1.
Okay.
So answering your question, and I kind of hope that there's a better argument, but I didn't find a better argument yet. Okay. So if I should say I didn't even type this up. I actually prepared these proofs for these lectures. I have to write this all up afterwards.
Okay.
And I hope in writing up I will be more effective. So the second lemma is that n is equal to 1, and so so what do we have here? Assume we have the tensor category of our ordinary modules. That means we have the tensor product of modules ls prime is equal as we have it, and our L1 is the VOA, the tensor unit. And we know that LS times a certain given module P is equal to NS times, NS times PS. And we also know that these PS and PS prime are non-isomorphic in decomposable modules. So really the setup again that we know. If we have all these conditions, then actually every NS has to be equal to 1. So that's the answer to your question. And let me and this follows by induction for N, induction for S, I mean. So the case S equals 1 is clear, but now and the induction step is a quick computation. So let me present this. So what do you have is you use one very special fusion rule, namely that that you only need this fusion rule. That's a one specific one. The standard representation times LS is LS minus 1 plus LS plus 1. And here I have to assume that S is not equal to W minus 1. But anyway, so then what can I do is what do I get is I get that NS plus 1 times PS plus 1 is equal to PS minus 1, because I already, by induction assumption, NS minus 1 is already equal to 1. And this has to be equal to NS times L2 times PS. And now we know that these summands are non-isomorphic, but one summand only appears with multiplicity 1. So this can only be true if this one here is equal to 1. So this is how you get this lemma. Okay. Yeah. So I tried always to be to give an overview at the beginning of lectures and then presenting more technical details at the end of the lectures. But let me now give you an overview what we have done over the last eight lecture hours. So we have achieved a few things. So we were looking at SL2 as an admissible level, and in the first part of the lecture I presented a classification of the abelian category. So we have full knowledge of this big category of SL2 modules at admissible level. Now, and this is the first step in this 3-step procedure. The next step is to get existence of tensor category, existence of vertex tensor category, and that's and then today I presented how to get some fusion rules. Now let's maybe recall how this things went. So the classification problem was as follows. Just because how it went, this is of course the interesting things of the whole story. So the classification problem was as follows. The simples was already done, mainly thanks to Coset and Redoubt. And this could be done by them because in a VOA you usually classify using Jou's technology. But Jou's technology only applies to simple modules and only applies to lower bounded modules. But it turns out simple module, any simple modules is a module is a spectral float twist of a lower bounded module, and this is why you can do this classification. The new result of Arakawa, Creutzig, and myself is that we get a full knowledge of the indecomposable modules. And how did we do this? We constructed as many indecomposable modules, as many extensions as possible. And then we derived as many criteria for vanishing of extension as we could. And then we proved that the data that we have already uniquely determines the category. So that means we did what we could and then did an exercise in homological algebra and we were done. The existence of vertex tensor category was quite a hard problem because the only existence criteria that we have apply to lower bounded modules, and the category is highly non-lower bounded. In fact, the existence results that we have only applies to C1 cofinite modules, and C1 cofinite modules are necessarily lower bounded and have finite dimensional conformity. In VOA, this is the tiny category of ordinary modules. So this is a priori quite bad, but then there's this really nice relation, these generalized Fagan-Frankel dualities that relate W algebras to W super algebras. And the trade-off is a super algebra is always maybe conceptually more difficult because the super has quite a few issues, but odd elements have a tendency to square to root 0, which means they have a more bigger likelihood to be lower bounded. And indeed, on the super side, that means the superside of SL2 is the n = 2 super Virasoro algebra. One can in fact prove that every module of interest is a C1 cofinite. And in particular, then one gets from this criterion of Jinwei and myself the existence of the tensor category, and then this correspondence, this duality between VOA and super VOA, between W super algebra, the n = 2 super Virasoro algebra, and affine VOA is so good that it transports tensor category structure. So that's how we get the tensor category. And then today I told you, well, fusion rules, we need ideas, and but it seems from the structural point of view, the first type of fusion rule one wants to have is one has the special category of ordinary modules, and one would like to understand how do ordinary modules act on any module. And this problem I was able to do by playing nicely with the Coset theorems that we have. And one important thing I think that you have heard is that you don't only have the usual cosets like SL2 times SL2 at level 1, the diagonal coset is Virasoro, but also these funny ones that come from this property that the quantum Hamiltonian reduction factor commutes with tensoring with integral representation, giving you, for example, that Virasoro times lattice VOA has a diagonal action of 2 Virasoros. It has a commuting action of 2 Virasoros, and that's in fact was quite necessary for determining these fusion rules. Okay, so this is what we achieved. So now, what did I not do? Let's see. There's one more thing I could have explained to you, but it would have taken another 2 hours, I would guess. Well, maybe not. The complete ribbon category, we would like to know this for all levels, but at least for 2 of those 2 levels, I mean -1/2 and -4/3, one can prove that every object is rigid, and one can determine all fusion rules so that one can be completely happy. And this will appear super soon, I think, because we are very, and so maybe if we are good next week on the archive, maybe in 2 weeks, maybe, I don't know, it's very far. So, and that uses another trick. And then another thing I did not explain is the Lindis formula. This is in fact how I came to the subject. So I visited David Ridout 9 years ago, or maybe 10 years ago in Australia. And at that time, we hadn't really thought about these admissible levels. Sorry, well, he had, but I didn't much. Anyway, we thought about, could it possibly be that the Lindis formula, that means modular transformation, gives you some nice information about fusion rule? Could this possibly make sense? And well, we discovered, yes, if you think about characters as distributions, then in fact you have a good modular group action on the characters of the big category, and this modular group action gives you a fusion kernel, you probably should call it, not a fusion coefficients, that give you good coefficients, good non-negative integer fusion rules. And in all computations that have been done, they do agree with our Lindis formula. So it's probably the optimal way to guess what the fusion rules should be. Anyway, I did not explain this. Main reason being it's 8-9 years old. I wanted to present something new, but it's a very interesting topic. So these are 2 old articles of David and myself, if you want to have a look. And then finally, let me give you so I think there are a few things one can do. So, and in fact, I'm very sure that one can do this. So there's an inductive procedure how you can prove understand categories, and so we understand it at these 2 levels, and what can shift the level by an integer, a positive integer, and it's still this. So I think, but it's in fact quite some work. But I think once this is all carefully written down, one can also determine the complete structure for K being the admissible level U over V, where V is either 2 or 3, and U is equal to -1 modulo V. Hopefully one can be even much better, but that would already be quite some progress, I would think so. And then one can do, and then let's say one can do a lot for various super algebras, and just because they inherit a lot of structure from S2, and in particular, I like D21 alpha a lot, and my master student is working on that. Devin, he might see here. I hope he's here. And then well, of course this is never nothing is ever the end of the story, but in order to complete SL2, I would say in general one needs to answer this question, whether every object is rigid, whether we have duality, whether we have a ribbon structure, and it would be also good to get a complete list, or a list of fusion rules that determine all of them. I think that both these problems are quite, really difficult, but or maybe, well, one needs a good idea. And for generic K, well, everything I've presented about the existence of vertex tensor of the C1 cofiniteness, these things didn't use admissible, and that's somehow kind of striking. And so I think one should ask the following question: one should study the category of C1 cofinite super Virasoro modules, so the super Virasoro this dual to the SL2, and what would one like to do is one wants this to be an abelian category that's closed under contragradient, and of finite length. And I think the main issue is the finite length issue, because so here there's one subtlety that I think is enormous, and namely for SL2 at admissible level, one knows that the center of the universal enveloping algebra acts semi-simply on the top level of lower bounded modules. Meaning, in other words, one knows that every lower bounded module has semi-simple action of the Virasoro zero mode. One knows that at admissible level. Now, if you look at modules of finite dimensional SL2, if you impose that the Casimir acts semi-simple, then you have a good problem. You can do a lot. If you don't impose this, then you have an enormous amount of extensions. So that means in particular, you will have infinite order extensions because you can zigzag around with extensions. And now I'm hoping that these modules will not be C1 cofinite. And I think if they are not, then it should follow that the category of C1 cofinite modules of the dual ones on the super Virasoro side are not C1 cofinite, and then it should follow that all the other properties that one needs are also satisfied, and then one would get tensor category for SL2 also at generic level, which would be, I think, quite spectacular, because it would be really unexpected. Good. I think I would like to stop here. Please ask questions, and in particular, ask questions on the outlook if you like. And thank you for your long patience.
Thank you.
Thank you very much. Very
Yeah.
nice lectures.
Yeah, in person would be probably much nicer, right?
Very nice.
Yeah, we really hope you can visit at some point. Hopefully
Yeah,
next year.
I've never been in China. So yeah, maybe next year.
So any more questions for Thomas? Yeah, if no